So exponential functions are of this form. However, give me 1 second. How about we do some, no, I don't want to import anything yet. I'm going to create a new one. All right. So let's compare some kinds of functions like f of x equals to 2x. F of x equals x squared. And f of x equals 2 to the x. These three functions look similar. They have a lot of stuff in common. However, they are so different. I mean, what do they have in common? The variable x and the number 2. However, the first one, 2x. That's a linear function. How do we know it's a linear function? Well, there's an invisible 1 power here. And well, that's how we know we have a linear function. X squared, well, that's a quadratic function and whose graph looks like a parabola, right? So that's quadratic. However, between the second and the third one, well, they could look alike by a lot. I mean, but it could be a little tricky here because in this case, well, they just look like reversed, right? Like, well, the second one is, which is a quadratic, we have x as the base and the number 2 as the power. However, the latter one, f of x equals 2 to the x, in this case, it's the variable that plays the role of the power and not anymore a number. So now we have a numerical base and the exponent is the variable. So, well, in this case, we call this exponential. Exponential. No, they're all functions, right? It's understood that they're functions. Well, to give you an idea of how they look like, how about we plot the three of them in the graphing calculator? All right, let me clear everything here. So that's 2x. That's x squared. And that's a 2 to the x. Again, they look similar, but I mean the position of the number, the position of the x really makes a whole difference. Graph, what do we have? Well, we have a linear, we have a parabola, and then we have the one that was outputted in black. Let me use a different color because so it doesn't get confused with the actual axis in this case. And also let me change the type of yes, I think this is the one, and okay. And let me make this green maybe. Oh, come on. I'm supposed to change colors here. And that's okay. And graph. Well, apparently the exponential and the quadratic one, they look apparently the same. I mean, at least just within the window that we are looking at these functions in, well, it appears that, however, well, we can always look at the table, second table, and see the values. Okay, again, the one in blue is a linear function, the one in red is a parabola, and the one in green is the exponential functions. And well, for really low values of x, notice how the y values are around the same. 2, 1, 2, 4, 4. Oh, they're the same for 2. They output the same y value. All right. However, when we get to like 4, 8, 16, 16, well, same. So it is the green one, the exponential one, the one that starts growing more rapidly for values of y. See the numbers 128, 256, 512, 1024, you know? So, and while when the exponential is already 1024 for x equals to 10, check how the linear is barely 10, and even the quadratic is barely 100. So this is the main difference between the three functions, even though they are they look similar, so to speak. Well, and well, so we have already talked about linear functions. Well, you guys have seen a lot of linear functions, how they are used to describe costs, for example. And that number multiplying the x is the rise over run, the ratio, which usually in the application for cost and economy is the price for an item, so to speak, right? And then we moved on, you got moved on to study quadratic functions. And well, those quadratic functions which depict parabolas, well, there's a couple of cases of parabolas opening up and parabolas opening down. And you might remember from back then that these type of functions are usually great to determine maximums and minimums, because in later applications when you take calculus more in particular, you will use those ideas to find maximums and minimums, to maximize a profit, to minimize your cost, to find the dimensions of a room that gives the maximum area. Well, you'll see if you have taken calculus already in high school, well, you know what I'm talking about. But that's more like generalized way. Now, what are exponential functions useful for? Well, so most likely when you read a magazine, read the news, or hear or watch TV, watch the news on TV, um, you might have heard of this term. Oh, it's growing exponentially. You know, when an illness, you know, it spreads exponentially. I mean, I don't think there's a. I think there's a pretty obvious situation that happened almost 3 years ago, right? We don't need to be very detailed about it. You know, with the pandemic, how it spread exponentially. So I mean, one contact and then two people then spread the virus, and then four, and then eight. So that's how it went, right? That's these exponential functions amongst, you know, the behavior of the spread of a sickness or a disease in this case. It's used. We use exponential functions. Oh, there's plenty of applications of exponential functions, such as population growth or decay. Well, depending on what you want to measure about a population, at what rate people is born or people is dying as well, right? But there's other applications to radioactive decay. You may have seen that before. If not, we're going to cover that later. And that radioactive decay and what else? The population growth, it's also used in chemistry a lot. So how many chemistry majors are here? Well, those of you are going to take physical chemistry. It was one of my favorites. Of my undergraduate was in chemistry, and in physical chemistry you do a lot of calculus, a lot of solving differential equations to describe how a chemical reaction, the rate of how reactant turns into product. And then there's other pretty cool systems in which you have a reactant, that reactant becomes an intermediate product, and then at the same time that initial product starts to show in the flash, well, it also disappears to form a second product. Those are called, well, sometimes depending on the situation, parallel, competitive, or even consecutive reaction. That's pretty cool stuff, and it actually relies a lot on exponential equations. So even what else? Electrical engineering majors will deal a lot with exponential functions to describe charges and voltages and a lot of pretty cool stuff. Well, of course, we're not gonna get that far in this course. I'm just giving you a brief overview of what is this huge field about of exponential functions. And like any other function, I mean, plug in values to x to get those values of y. I mean, there's really no difference in the way how we work with those exponential functions. And well, so we already saw the graph in our graphing calculator and later before. Well, so here we have the generic forms of these exponential functions. And by the way, there's a little typo here already. Let me stick with f of x b to the x. So I had c a to the x because that's I was using my notes from when I make these notes out of a different book, but it's gonna be essentially the same thing anyway. So how do we make a distinction between this graph and that graph algebraically, first of all? Well, notice we have an integer raised to a power x. How about we evaluate some values, I mean. Okay, so for example, f of 0, it's 2 to the 0 power, f of 1, 2 to the first power, f of 2, 2 to the third power, second power, not to the third. Where did that 3 come from? F of 3, 2 to the third. Well, any number to the 0 power, we know it's 1. That's a 2. That's 4. That's 8, etc. Right? Powers of 2, 0, 2, 4, 8, 16, 32, 50, 32, 64, 128, etc., etc. Well, what about, well, notice how these numbers, they get bigger for larger values of x. And I mean, we can see that from the graph right here, all right? We can see it right here. I mean, let me just make an estimate, because, well, 0 is 1, 1 is 2, I'm going to say here, 2 equal to 4 maybe here. Well, we wouldn't be able to see 8, right? But I mean, it's consistent with what we have with the calculations. All right. So that's as far as the first case in which the values get bigger and bigger. Well, there's actually this corresponding lingo to that. We'll do that in a second. Now let's have a look at the other example, at the other graph, with the other function. Well, over here we have 2 to the x, but over there we have 1/2 to the x. So in this case, okay, let's get some values of y. Let's evaluate some. That's f of 0 equals 1/2 raised to the 0 power. F of 1, that's 1/2 to the first power. F of 2, that's 1/2 to the second power. And f of 3, that's 1/2 to the third power. And yes, I mean, we are still going to square, cube, raised to the 4, raised to the 5th, etc. However, notice that the denominator in this case is the one that gets larger and larger every time we plug in a whole new value of x. Well, I mean, same story for the first value, f of 0. I mean, any number, any quantity to the 0 power is always 1. Any quantity to the first power is itself the quantity, 1/2. Well, here is where we are going to do some calculations. 1/2, that's the same. We can also think of lots of exponents. 1 to the second power, 2 to the second power. Well, 1 to the second power is still 1. 2 to the second power is 4. Well, this is 0.5. This is 0.25. And that's a 1/8, which is 0.125. All right. And well, we don't need to compute even more. I think we're fine with these values. Now, what's happening here? Well, let me make some space here. And in this case, they get smaller every time. Well, like I mentioned before, there's actual formal vocabulary to this. And well, the formal vocabulary in this case is that this function is increasing, whereas the second case is that of a decreasing. It's a decreasing function in this case, right? Yeah, they get big, smaller. Well, no, we use the vocabulary. Well, Anything? Oh, so essentially, we are raising an integer, a big number, right, to a power that should get bigger and bigger and bigger. But in the other case, like in the second case, 1/2 to the x, we have a really small, a tiny number getting multiplied by itself. So like half of the half of the half of the half. So every time, this is every time getting, like tinier and tinier and tinier every time, like for example, so if I have this square, right? If I divide this by a half, well, half, and then half of it, and then half of it, half, half, half. These are called fractals. You may have heard about them. Fractals, have you heard of them? Yep. There's other fractals for like divisions by 3, for example, for triangles, and for example the 1/4 to the end. That is essentially you divide everything by 4, and there's a couple of ways to divide the 1/4 by a geometric shape into 4. We can do the square, 4, 4, 4. Yes, it gets hard every time because of the pixel size. And the other one that you may be familiar with is the triangle. We can divide it into 4, and it looks like the Triforce, right? Yeah, and we can still do the same over here. Another one. Well, it's kind of hard to do, but I mean, you get the picture, right? So that's one of the many applications of exponential functions. There's also this thing called mathematical art, which relies on geometric patterns based on certain mathematical models that in this case, give rise to fractals and other pretty cool shapes. I believe UCSD has like a division of mathematical art there. It's pretty cool. So, well, let's see. Of course. Well, let's look at this graph and think about its properties. Okay, number one is the graph of is this graph even a function? Why so? Passes the vertical line test. That's good. That's number one. Is that function furthermore? Is it one-to-one? It's one-to-one because passes the horizontal line test. All right. So, and that's all. That's the most important thing. The fact that it's one-to-one, because then this exponential function will have an inverse, and well, it's not like I'm going to spoil anything. It's called the logarithmic function, and well, you'll see how is that going to work later. Domain. Let's look at the domain. What would be the domain given this graph? All real numbers. All right. What about the range? 0 to positive infinity. However, is the 0 included here? No, it's not. Actually, that's what you didn't see before. So, because in this case, the exponential is never 0, and that's something that we will justify discover anyway. Algebraically, well, it turns out that the exponential function has a horizontal asymptote. That is, this exponential function never touches the 0. Well, where have we seen this? Well, again, exponential functions, amongst many other things, are used to model population growth and decay. Let's talk about population decay and how can we connect this? Well, I mean, during the pandemic, yes, I mean, yeah. So we use a lot of Lysol, remember, to clean everything up? But you might remember seeing the label kills 99.99% of the virus or bacteria, right? That's because population is never going to be 0. So we can see that in those cleaning supplies, all right? So they're not guaranteed to clean 100% of the bacteria or virus. So that's why. Okay, let's look at these properties. And yes, so the domain is all real numbers. and the range is from 0 to infinity, and be careful with the 0. The 0 is not included in the domain. That's why we have that parenthesis, and in fact it goes asymptotically to 0. The x-axis is it's a horizontal asymptote, and it's 1 to 1. Yes, because it passes the horizontal line test in the same way that it passes the vertical line test. Well, we're going to graph exponential functions, and we're going to talk about the number e. Well, 4 to the x minus 2. So they're asking us to graph this function, 4 to the x minus 2, and also state the domain and the range. All right. So, as you could tell from the previous examples, it's not that easy to graph exponential equations, especially because either these functions get really, really big very rapidly or get really, really small very rapidly, and it's kind of hard to plot those decimals or plot those big numbers. And usually we work with grids that are 10 by 10. Well, in my case here I have a 7 by 7. However, we're going to use shiftings and transformations to graph this function, which is a lot easier. And I mean, in the same way that we did these shiftings and transformations for the rational function last week, it works the same. I mean, there's a whole section about this transformation, starting with the library of functions such as the parabola, the linear, the exponential, the rational, the radical, and shiftings work the same for every single function. Well, in this case, 4 to the x, 2 to the x, 7 to the x, 5 to the x, well, they are going to have approximately the same shape. And in this case, we are not really looking at precise values. I mean, if you want, why not? Let's plot some. So 2 to the x, 5 to the x, I don't know, maybe 7 to the x. Let's graph them and see the differences. Well, all we can see right here is that the bigger the base, I mean, it goes from 4 and then, what was that? 6 and 7, right? No, it was 2, 5, and 7. 2, 5, and 7. Well, so all we're doing here is raise 7s to the same powers as the other functions, and because it's a larger number, it's going to grow a lot more rapidly, more quickly than in comparison with the other exponential functions. But essentially, the shapes of these functions are similar, and they also happen to have the same asymptotic behavior as far as larger values of x, or really, in this case, really small numbers of x. You know, it goes to negative infinity, never touching actually the 0. Even though, yes, the calculator is showing us an intersection with the x-axis, but no, there's actually a horizontal asymptote there. Yes?
What about 1 to the power of x?
That's an interesting one. Why not? Let's see what happens with that one. 1. It's just a horizontal line because, 1 to the second power, that's 1 times 1, which is 1. 1 to the fifth power, 1 times 1 times 1 times 1 times 1. That's multiplying it 5 times. 1 to the 5,093, it's still 1, all right? And it's going to remain a 1, which is y equals 1. That's a horizontal line. Good question. And it's actually one of the restrictions of the exponential functions that, let me go back. The fact that, yes, it's right here, right? B cannot be 1 because for the case in which B is 1, what we have? A horizontal line, all right? And it's also greater than 0. The negative cases, let's forget about those. I mean, let's just consider the cases in which B is positive and not equal to 1. That is from 1.0000001 to your favorite number. Let's see what happens with that one. How about 1.001? raised to the x. Well, I would let me delete some zeros. I think I kind of exaggerated here. Delete. No, yeah, that's fine. So do you? Oh, it's also it's this green. I mean, it's exponential, but it's really it's growing really slowly in comparison with integer bases, right? So, but still, at least it's a number greater than one and not a number less than one. All right. So let's see. Yes, graphing. So regardless of the integer base in this case, well, I'm just going to draw a generic graph, which is going to look like this, with with a horizontal asymptote coinciding with the actual x-axis. All right. Well, using shiftings and transformations, we can pretend that we don't have the -2 essentially. So its parent graph f of x 4 to the x, which is the graph I have over here, all right? However, this -2, this -2 right here will will describe a vertical shift. And how do I know it's a vertical shift? Because it's a function f of x, whatever it is, plus or minus a number, like plus or minus k, if you will. And well, when it comes to vertical shiftings, the number of units that we will shift that graph, it's going to go in the direction of the sign. In this case, since it's negative, that means it's going to be shifted 2 units, but down in this case. However, if we had this -2 in the exponent, that would have described or denoted horizontal shifting. And well, so in this case, let's see. This -2 means shift down 2 units. Well, and all we can do, I'm going to graph this graph along with its horizontal asymptote, and I'm going to shift this 2 units down. All right? And that's all it does. That's about it. So make sure to shift not only the graph, but also the asymptote. It's very important, because if you just shift down the graph, it's going to look like the graph of the exponential would be intersecting with the horizontal asymptote. And it's not the case that the exponential function intersects its horizontal asymptote as opposed to rational functions like we did last week. They do intersect their own horizontal asymptotes. All right, so that's one very brief example to begin with, just one shifting. Let's look at another example. Oh yes, this one has 2 shiftings in this case, right? There's 2 transformations here. And how do we know that? Well, because in this case, we can ignore the -2 in the exponent, and we can also ignore the +3 as an independent term. Well, in this case, it's the graph of 2 to the x shifted, well, 3 units, blank, and 2 units, blank. All right, let's fill in the blanks. So it's going to be 3 units in which direction? Up. Mm-hmm. And 2 units in which direction? To the right. Yes, that's right. Let's go ahead and do that. And well, what's going to be our starting point? Well, the same generic graph. Notice for the generic graph, It will always, oh well, this one is shifted already, but well, it will always have the point 0, 1 as the horizontal, no, as the y-intercept, regardless of the base. 2 to the x, 7 to the x, a million to the x. Evaluated at 0, the net number to the 0 power is going to be 1, which will be consistent with the order pair 0, 0, 1. Well, I mean, check this out. Don't we have the same point 0, 1 for all these graphs of the exponential function, regardless of the base? All right. So just start with a very generic graph. So without touching the x-axis, make it increasing. Make sure to cross the point 0, 0, 1. And the horizontal asymptote. So notice this time I actually put a dot on the y-intercept because we could use that point as a reference to do the translations and the shiftings. Well, how is that going to work anyway? Because let's keep an eye on this point. What I'm going to do, okay, let me hold on the whole graph. And I'm going to focus on this point. I'm going to shift it 3 units up. So that's going to become a 4. And then I'm going to shift it 2 units to the right. And that's how the graph is going to look like this time. 2 units up, and 3 units up and 4 and 2 units to the right. All right, so that's the new graph. That's the translated graph. That's pretty much it. However, I would like to go back to the previous example because there was more about it. I didn't state the domain and the range. All right, so the domain, it's still the same. It's all real numbers. Negative infinity to positive infinity. And I'm going to write both versions of the notation, the interval notation as well as the set builder notation. That's x such that x belongs to the set of all real numbers. That's the fancy way to say all real numbers. And the range. The range, well, originally, the range of the exponential function goes from 0 exclusive all the way to positive infinity. However, because we shifted this graph down to units, that shifting also has an effect on the range. Well, I don't want to, hold on. So in this case, it's going to go this time from -2 to positive infinity. Or in set builder notation, y such that y is greater than -2. All right, set builder notation and interval notation. You may be asked to give your answer in either one of those notations, or maybe even both on the homework or on an exam or quiz. All right, so it's important to keep in mind both ways. All right, yes. Let's look at the next example and the domain. Again, the domain is all real numbers. That doesn't change. The domain is always the same for an exponential function, regardless of the shifting. If it's upside down, if it's reverse, if it's increasing, decreasing, it really doesn't matter at all. However, the shifting of an exponential function has an effect on its range. All right, so range in this case, well, that 0 got shifted 3 units up, so that's going to go 3 to infinity, or in the fancy curly brace notation. Oops, no. like this. All right. It's only the vertical shifting what has an effect on the range, not on the domain. Horizontal shifting, no effects at all on its domain and range. All right, let's see what's next. The exponential function e to the x. Well, so this is a very, very special kind of function. The number e, which is approximately 2.7182 plus decimals. Well, I'm going to use equal sign because if I'm using decimals, I'm indicating that the number goes on forever. So I'm going to keep this an equal sign. And that's a transcendental number in a very similar way than pi. You know, pi is 3.1415 and well, in many, many, many decimals. I don't know how many million decimals have they discovered up to date, but they have discovered a lot. There's computers that can compute, they're actually in charge of doing all these computations. But I mean, for practical purposes, we use pi as 3.14, 3.14 is the most common one to use, ultimately. All right? And same for the exponential. Although the third digit is an 82, we usually use 2.71 for e, even though technically we should use 2.72 because of the rounding rules. But it's very common to use just as to regard e as 2.71, and this is called Euler's number. Yes, so I know it's pronounced, it's spelled like Euler, but it's actually pronounced Euler, right? So essentially, well, when we do e to the first, e to the second, e to the third, e to the fourth, what do we get? Well, in this case, we are going to raise a number containing decimals to a power. Well, that's not something we can do in our heads, as opposed to the previous kind of exponential functions like 2 to the x, 4 to the x. Those are doable by hand. Those are more manageable. I mean, we still get really, really big numbers for the minute we get to get to plug in values of x that start getting big. However, well, it's not that easy with the exponential, with the base e function. Let me clear, and I'm just going to leave the e to the x. And well, for those of you who use the the TI calculator, to reach the exponential function, we use the ln button. Here, notice e to the x is in blue. So the fact that it's blue, that means that we need to use the second function so we can actually reach the functions in blue. So, whoops. And e to the x. All right, just very simple, very generic. I mean, no shiftings here, no coefficients at all. And let's look at the graph. I mean, the graph doesn't look any much different than, for example, it's pretty close to 2 to the x or 3 to the x. Well, because it's actually e to the x, the number e is between 2 and 3. It's 2.71. Well, what about the values that this function outputs? I mean, there's no integers as outputs. All right, so when it comes to working with the exponential function of base e, that's how we call it, or the natural exponential function, that's how we call it as well, in a similar way than the natural log, because the natural log is it's a logarithmic function whose base is the exponential or the natural exponential. We will discuss more in depth about this relation later. And well, we got to see these values in the calculator. No need to write them again, so you get an idea. And I mean, just draw any exponential function. with this horizontal asymptote. All right. Let's see. Let's see what's next.